Okay, so this is, I intended it to basically make sure that everybody who comes to my afternoon talk has all the background necessary to fully understand what I'll be saying, take full advantage of it, but I hope that this will stand alone as just an explanation of a classic C++ concurrency. This is what we know how to do things. Now, a little bit of kind of explanation of why I'm coming back to this. You know, this isn't exactly the hot material right now. So why now? Almost 10 years ago, I gave this talk at CPPCon about atomics, and since then, nothing has really changed in a way of, like, C++ added some extra stuff, but fundamentally, you know, more of the same. The only thing that changed was that, like, most of what I was saying about how to do things fast is actually wrong. So this is basically the message that 10 years ago, I wasn't the only one, of course, you know, everybody was saying this. Write your most demanding code log-free. Log-free is hard to do. Isolate it to where you absolutely need it. And the most demanding is typically highest contention. Now, I'm simplifying, but that's the basic idea. This is where we're at today. So the bottom line with the circles, that's this here. That's the spin lock. It's not stud mutex, although it could have been. It is a kind, but it is a mutex. It has full mutex semantics. That's actually x86 machine at Intel. This is Apple Silicon. So even stud mutex, we've had a talk yesterday, which actually shows, like, essentially this part of the chart. Even stud mutex beats atomic fetch-add on Apple. Apple Silicon is somewhat unique in this regard, but with respect to stud mutex, not with respect, I mean, spin lock is still sitting here and untouchable by everybody. So this changeover of what's faster, what's slower, that's what prompted me to come back to it. And, you know, now I need to basically go over, like, all the background for what's going on here. And two things go on here, basically. There is concurrency and there is memory model. So that's what we're going to to deal with in this talk. Now, ground rules and basics. So concurrency is not parallelism. Parallelism is mostly about algorithms and data partitioning, dividing the work, getting the work done in parallel. Concurrency, that's all about threads, and how to synchronize them, how they interact with each other. Thread, when we talk about, intuitively everybody understands what thread is. There are several popular definitions. One of the classic ones, sequence of programming instructions that can be managed independently. Usually the managing part is done by the OS, but actually doesn't have to be. Interaction between two threads, so managed independently. If they do interact with each other, it happens through memory. And the fundamental rule of that interaction is that accessing the same memory location from multiple threads without some sort of exclusive access guarantee, and that's a very vague, hand-waving thing, we'll explain later what it is. Without exclusive guarantee is undefined behavior, except when all accesses are non-modifying. We're going to talk a lot about what makes your programs fast, so we need to also define performance and efficiency. Efficiency is exclusively about the use of resources, and there are basically two parts to it. Using all available resources at all times, that's the maximum efficiency, and not doing any work you don't need to do. It doesn't actually, strictly speaking, it doesn't have anything to do with performance, because performance is always defined with respect to metrics. So throughput is, in HPC, throughput is a classic performance metric. But in embedded systems, power is a more important one. That actually comes up later, it's important. Latency in many applications is the more important metric than throughput. In some applications, accuracy is a performance target because there are situations where your calculations are approximate. And that's okay. And achieving certain accuracy is one of the performance targets. The first rule of performance is to never guess about performance. Performance must always be measured. There's actually a second rule of performance. Everyone knows the second rule of performance? So this one is better known. Second rule of performance is programs can be a lot faster if they don't also have to be correct. Now, when it comes to correctness in the context of concurrency, there is fundamentally this thing. Accessing the same memory location from multiple threads without exclusion is UB. Locks give you that exclusion. That's basically their purpose in life. Okay, is there anything else? Do we need to know anything else? To write correct code, not really. To write efficient or high-performing code, well, high-performing code depends on your performance targets. Efficient code, yes. Okay, so now let's go into the building blocks of C++ concurrency. So we have these atomic operations. Atomic operation is an operation that is guaranteed to execute as a single transaction. So it's something that cannot be interrupted. All other threads will see the state of the system either as it was before or as it was after, but they cannot observe the system in its intermediate state. That's actually a very generic concept. It applies at the hardware level to instructions. It applies all the ways to systems such as databases. So that concept of atomicity. In our case, we'll be actually interested in atomic operations. So why do we need that? Well, here is an integer. We are counting on two threads. That plus plus is what's called read, modify, write operation. That term will appear many times. It's important the distinction from other operations. It reads x from memory, adds 1, writes x to memory. The problem, and that's where the need for atomics comes up, is both threads can read it, both threads can modify it, both threads can write it, you end up with 1. So that's what we call the data race, a particular form of undefined behavior. Now, C++ actually doesn't say that that's the bad thing is gonna, it just says that behavior is undefined. But at the hardware level, yeah, that's what's gonna happen to you. Okay, why does it happen this way? I'll give you kind of a more rigorous explanation, but at the sort of cartoonish level, looks like this. Your entire memory subsystem has the main memory, has multiple levels of cache, has multiple cores, and some of these caches are per core and some are shared between different cores. And so when you, the CPU itself can only access its closest cache, L1 cache, this one here. So when two cores read the value of x, they just read it from their private per core caches. They don't know anything about each other. They increment it, and then they write it. And when two cores end up with different values, one of them will be eventually committed to memory, and you'll end up with, so one of them will be committed first, the other one will be committed second, overwrites the first one, but you end up with 1, because they didn't wait for each other. Now, at the same time, there is also another component to the question of visibility. So let's say we have the third core that is observing things. What is it going to see? Well, without atomic guarantees, it can see anything. It could observe the 1, it could fail to observe 1 and observe the 2, anything's possible. All right, so here is your exclusive access to shared data. You put the mutex on it, you guard your increment with the mutex. This is correct, this works. Here is another way. I'll explain more about what this does, but we have this thing in C++ stood atomic. It makes your variable atomic, it makes operations on it atomic. There is a big caveat on that we'll go into, but for now, stay with me. It makes operations atomic. So now plus plus is atomic. How does it actually work? Well, it's a single non-interruptible transaction. Conceptually, it punches all the way through to main memory. Nobody else can observe the intermediate state of the system while that is going on. So conceptually, I'll explain what the hardware really does, but it behaves as if this was true. So this is locked now. When you want to do, when the second core wants to do an operation, it acquires the lock on the memory location. It does its operation, the results trickle through caches. When it's done, it's unlocked, the atomic transaction committed. If somebody wants to observe, they have to wait for the lock to be released. Now they can see only the final state. So that's basically what atomics do for you at the C++ level. All right. Atomics are not enough to write correct programs. That's a lot of people miss that. In practice, you know what to do, so you don't miss it in practical terms. But it's tends to be excluded from the explanation. And let me show you what's missing, what's implied. Let's look at this code. Here is mutex, and it guards this variable. Now, what's inside mutex? Well, anything. There are multiple ways to do this, but in general, inside this mutex, there will be an atomic flag, and let's say it's an int, and let's say we'll call it locked, and 0 means it's not locked, 1 means it's locked. Odds are good your stud mutex actually has that in it somewhere. It's not the only way to do it, but it's the most common one. It has other stuff, but it has this at its core. So now here is our code that increments the loop lock and unlock. Everybody agrees that this is correct. Didn't say anything about performing. Correct, yes? Yeah. Yes, it is correct. No catch here. Notice that M and X are completely different variables. There is no, okay, you don't know what's inside of M, but let's just say that it's that locked flag, that's what's inside of M. There is no way M, operating on M, has anything to do with X. So they're completely independent operations. C++ compilers live to do that sort of stuff. That's the classic optimization. Hoisting expressions out of the loop, as well as doing basically compile time calculations when possible. This would actually be very bad if it really happened to us. But if you write this code, and if M wasn't a mutex, but just some struct with an integer called locked, this is exactly what the compiler would do. Well, one of the things it could do. It's perfectly valid from C++ point of view. Calling it locked and calling it stud mutex by itself doesn't mean anything. So something else prevents the compiler from doing this only for stud mutex. So what is it, and what's what makes stud mutex special, different from struct M? Oh, okay. What it is the memory model. Basically, that distinction comes down to the definition of the memory model. There are several different ways to talk about the memory model, and I'm going to talk about it not in the language that C++ standard uses. I'll introduce that language a little bit later. There are several different ways, and they're all equivalent. They all talk about the same thing. But I'll use the language of memory barriers. So, memory barriers are part of synchronization. So memory barriers are what prevents basically this from happening. You can't really synchronize data accesses, even with atomics, even with mutexes, if you didn't have a way to control the order of memory accesses. So something has to force the compiler and then the hardware, and that's actually the trickier part. Compiler operates by the language. We can define rules in the language. We can just say stud mutex is special, don't do this. It's a fragile way of doing things, but it's but it would work for that particular program. Well, hardware doesn't care what it was called. So we need some way of controlling the order of memory accesses. It's global because it's across all the CPUs on the shared memory system. And that's what memory barriers do. They always have hardware support of some sort. They are usually invoked either through specialized CPU instructions or through modifiers on other instructions. They're often attributes on operations that interact with memory, reads, writes, things like that. Okay, so why do we need memory barriers? Well, we've seen this compiler optimization for mutex, but let's say we can stop. So you can do a lot of things to your compiler by declaring things volatile in C++. The compiler basically has to respect the order of modification of volatile. By the time you get to assembly, there is no trace of that volatile. If you take some code, slap volatile on it, it will look at the instructions and then remove the volatile. Compiler might optimize it, but let's say it doesn't. Assembly is exactly the same. There is no way to convey the word volatile in assembly code. So let's say this is, so we have some variables, A, B, C. We have an atomic variable x. And this is in program order, we operate on A, on B, so we write them. C, then we modify X, and again write A, write B. That's the program order. That's the instructions as they're written. This is the observed order. And what do I mean by observed? There are, so there is another core, it reads these values, and if this write, if what it reads here is the same as this, we say that this write was observed. Yes?
It's just, it's hard to see your mouse if you're pointing at anything.
Okay, so, all right, I'll say. So here we read A, the first read of A. If we see the value that was written by the first write of A, we say that this write was observed. If we see the previous value, we say it wasn't observed yet. Now, there is a trivial reason why it wasn't observed yet, because it hasn't happened yet. Two separate cores. I'm drawing them like this, but there isn't actually a global clock. Well, there is a system clock, but it's not relevant to, nobody is looking at that clock at this time. So the first thing we must agree on is, what does it mean to be now? And the way we define now in all these models is through this atomic variable. So here is the write of x. Yeah?
Sorry, could you maybe point on the screen? I think your cursor is not visible.
Oh, okay. All right. Okay, so this is the x is atomic variable. We write into x, yes? Mm-hmm. And the other core is watching x. At the moment you see x change, we declare our clock synchronized. We say, okay, this is now. Now, like at time equals 0, I wrote x. When I observe this change, I call time equals 0 on this other thread. So now I have that one point where I agree about one event that is simultaneous. Everything else I'm going to build from that point backwards in time and forwards in time. Again, this is not how the standard talks about it, but I find this language easier. Okay, so now we have, remember, this is no memory barriers, or in C++ we call it relaxed memory order, same thing. No memory barriers. So this is now, that's where we saw x change. There is some order of modification of these other variables. And there is some order in which we observe them. So this arrow means that I keep reading B, and this is the first time I see this result. And I keep reading A, and this is the first time I see this result. Without memory barriers, there is absolutely no guarantees on the order in which these writes make their way to that other thread. So here are some writes that happened before x was modified. This is program order. This is real. This is how, this is, yes?
So You are talking about ARM, right? Because
I'm talking about C++ memory model.
okay, so when you say memory barrier, so you are talking about when compiler do not put things out of order. That
No, see, this is program order. So this is already machine code. This is what whatever the compiler did. This is the order of instructions.
okay. So if the order of instruction is not jumbled up by the compiler,
It may or may not be jumbled up. Doesn't matter. For whatever reason, this compiler generated this order. That may be the output of the jumbling. Doesn't matter. But this is a machine code. This is what the core actually executes. So compiler at this point doesn't. Maybe this is a jumbled order, but this is like if you actually disassemble your object code, you're gonna see these.
so if it is jumbled up, if it is not jumbled up by the compiler, then x86 will show no error at all. So if only if
Again,
compiler-
I'm going by what's called C++ virtual machine. These are the guarantees that the language itself gives you. On any hardware, so hardware may give you additional guarantees. C++ has what's called the C++ virtual machine that operates according only to the guarantees that the standard itself provides. So we have now this hardware that has no additional guarantees. Well, that is the C++ virtual machine. C++ virtual machine gives you only the guarantees specified in the standard and no other guarantees. That's the only thing you can count on in a portable program. So I'm explaining what the standard, C++ standard says. C++ standard says, okay, this is the program order, and yes, this is the result of the compiler optimization. After everything the compiler done, this is the program order. This is what's observed. So we saw X change. And before X changed, we wrote C. If we try to read C on this other thread, we may not observe that new value until after X changed. So this basically, essentially the visibility of this change moved past the atomic change. So the write happened in the past, because remember, this is now. The write happened in the past, but the observation happens in the future.
It's basically inconsistent view between the two threads, the writing
Yes.
thread and the reading
So
thread.
there is so C++ standard talks about memory order. I'm using the word barriers. There is yet a third language that I don't want to confuse you with, but that's memory visibility. So that talks about what's visible, the views. And you can express this whole thing just by talking about what's visible. And yes, so it is an inconsistent view. At any moment in time, if you take the snapshot of memory from this thread and it takes snapshot of memory from this thread, they would disagree about what the memory looks like. The only thing they agree on is at the time equals 0, the X value was whatever you wrote. That's the only thing they agree on. Everything else they can disagree on. Okay, we have a full memory barrier. And okay, in C++ terms, this is actually what's called acquire-release memory barrier. Full memory barrier. Full memory barrier says that if this is now, if this is when I saw X change, everything that was visible, that was done in the past, became visible in some possibly different order, but in the past. So if I could take an instant snapshot of all the memory here, an instant snapshot of all the memory here, those would be consistent. The order in which they became consistent could be different. But the whole snapshot would be consistent at this moment in time. I would not see any of these changes that in program order happens in the future. They cannot trickle into here. I would see all of these changes that in program order happened in the past. They would not be deferred until here. That's the guarantee of the full memory barrier. After you cross the barrier, again, everything is unknown. So if you're waiting to observe the results of this write of A and this write of B, they could, for example, be visible out of order. First you see B change, then you see A change. Because there are no barriers here. But this divides the past from the future. Okay, is that clear? Okay, so full barrier in C++ terms, acquire-release barrier. Guarantees that all memory operations scheduled in program order before the barrier become visible before the barrier, and all the ones scheduled after the barrier become visible after the barrier. All operations, reads and writes. All operations, not just operations on the same atomic. All operations. Now, the important part is it's not a kind of global system push. It only works for the threads that participated in the barrier. If you have another thread, well, 1 second. If you had another thread that did not issue that barrier instruction, whatever it is, no guarantees are given. Okay, please.
Does it mean we can have a race condition on the barriers themselves?
What do you mean?
If two threads issue memory barriers?
Well, okay, kind of. See, it depends on what you're doing with this. So that's more of a question of like whether your code is correctly arranged. So the way you synchronize your clocks is you're watching for that change to happen. So one thread writes with the barrier, the other thread reads with the barrier. If they both write, of course, there will be, one of them will stomp on the other. But that's kind of a question to basically the logic of your synchronization, what you're trying to synchronize. You have to agree on what now means. And for that, the only way to do this is to use one atomic variable as the clock and watch it change.
Got it.
Now, C++ actually doesn't say anything about now. It says it only uses this happens before and happens after, and turns out that that's enough to build the whole rigorous formal picture of it. How do, happens before what, happens after what? Well, again, it actually implicitly uses atomic variables as clocks. So when you see a change in atomic variable, now you can say, okay, if on thread 1 something happened before I changed my atomic variable, and thread 2 saw me change that atomic variable, now I can say what happens after I change that atomic variable. So that's basically how this machinery works. Yeah?
So the full barrier is sequential consistency, right?
No, sequential consistency gives you additional guarantee, which I'll mention.
Yeah.
This is acquire release.
But will it still be fine if two different, will it be fine in global scope where multiple threads are trying to have full barrier, like making sure the overall read-write cannot be moved before acquire or after release?
Yes, that part will be fine. Okay, hold on to that question. I'll explain the difference between acquire release and sequential consistency. But so sequential consistency barrier has some additional guarantees built into it. But so far what we're talking about is really acquire release barrier. Now, there are situations, and we'll see one very soon. We actually have seen that situation, we just didn't know, where you do not need a full memory barrier. Here is the simplest example. Okay, so I have some object, I have an atomic pointer to this object. I am going to construct it here, and then, so at this, this is a local variable, so nobody can see what I'm doing here. This is all private to this thread, nothing is being shared. But here I'm actually, the atomic is global. The whole point of atomic is other threads can see it. So at this point I'm storing this pointer into the atomic, I'm publishing my object. It would be really nice if anybody who acquires access to this object through the pointer P would actually saw it in its constructed state as opposed to in its half-constructed state. So again, the same issue. What guarantees that, so construction did some memory installation, there were some writes here. How do we guarantee that these writes become visible when by the time you read from P. Now, if you say P was null, I published non-null. If you read from P and you get null, then we call it you're still in the past. You're before now. You haven't seen atomic change. But the moment you observe that P changed to something that is not null, that's when our clocks are synchronized. On one thread, I published at the moment time equals 0. On the other thread, when I saw the non-null value of P, I was okay, now is T equals 0. It was published. Construction happened in the past. It would be really nice if it stayed in the past. Yes?
Maybe this is a slight misunderstanding on my part, but because you're storing this to an atomic itself, wouldn't that be visible as a whole? Because on x86 you get exclusive access to that to the cache
On all
set.
systems, you have exclusive access to the atomic.
Yeah.
Nobody said anything. See, what's inside T is not this.
Yeah.
So nobody said anything about you have exclusive access to this.
Yeah.
But these are, remember that picture with multiple caches.
Yeah.
All of these are sitting in L1 on one core.
Yep.
Nobody said anything about them making their way to main memory and from there to the second core. So that's the problem. You have the entirely constructed object sitting in L1 cache and other cores can't get to it. So you need some guarantee to prevent that from happening. And that's what the barriers do.
In this case,
So I think, sorry, for your thing, it guarantees you see the correct pointer, but what it points to may not be constructed when you see it.
Yes, if you didn't have any memory barriers, this variable, atomic variable, is the only guarantee you have. It will atomically change from non-null to null. You will see either null or the correct value.
but in this case isn't the construction and if we're talking in a thread order, it's all sequential in this case. Like
On
when you write the atomic, obviously.
On the thread that writes it, yes, but remember, memory visibility on different threads.
Yeah.
Without barriers, there are no guarantees at all on what becomes visible.
Like another thread before the store happens would read null, right? And
Before the store, it would read null, but after the store, it would read not null.
Yep.
But it's entirely valid within cplusplus virtual memory machine. It's entirely valid for that to be the only visible thing in the entire universe.
Okay.
Yeah, it's not null, and that's the only thing you can see. Everything else is still visible in its old state.
So the construction itself could be in the view of like either the compiler or the CPU could be reordered in this case.
Yes.
Okay.
Yes.
Sorry.
Yes, so the entire construction hasn't become visible yet. What you need is a memory barrier, but you actually don't need the full memory barrier because you don't care about what happens after the store. You only care about what happens before the store, so you need what's called a half barrier. This is the release barrier. All operations executed before the atomic operation must become visible to the other side. And I'm intentionally being a little bit fuzzy here, but before they observe basically this P changing. So at the moment when the other thread sees P change from not null to null, they will have a guarantee that their view of the memory includes everything that was done on the publishing thread before this moment. Nothing about after, but before, all of this is visible. So this is the release barrier. So here is how it works. This is when you saw atomic change. This is where we wrote the atomic. This is when you saw it change. So this is what we call time equals 0. So all of these writes are observable to you. They became visible at some point before this barrier. So if you read before the barrier, you see some of them happen, some of them didn't happen yet. You can see an inconsistency. But whatever you read after the barrier, all of these changes are visible to you. So this guarantees that you published your object. You made it visible fully. Yes?
But this also says that if you make changes to the object afterwards, you could potentially see that too.
Yes. Yes. So that's why there are synchronization schemas that rely just on this simple protocol, publish P atomically. In those schemes, release barriers are used in a lot of things. We'll get to the kind of more complex picture. But if you build a publishing protocol that just uses this release and acquire the other side, you may not change the object after you published it. You make all your changes. RCU works like that. You want to change it, you prepare another one, and then you atomically publish that. And now anybody who reads it will see the new one. Anybody who read in the past the old one still sees the old one. But yeah, you cannot change that object. Okay, acquire memory barrier is kind of the other side of the release barrier. So remember I told you at the beginning that when we talked about full barrier, that full barrier only helps if both threads issue it. The same is true for this. So if one thread did the publishing with the release, and the other thread just looks at the value of the atomic pointer and says, oh, it changed, that's it. I'm going to dereference it. Nothing is guaranteed. Okay? There must be a corresponding barrier on both threads, and on the reader thread, so this is my reader thread. I'm reading this pointer, and if it's not null, I'm going to dereference it. If it's null, then I'm still in the past. Object hasn't happened yet. I don't know, keep reading it or whatever. This is done by the acquire barrier, and that works in the opposite direction of the release barrier, like this. So acquire barrier guarantees that none of these before can move into after. These can move here. It's kind of like it makes a lot more sense when you put them both together. And when you put them both together, it looks like this. So a thread comes in, and well, let's start from the middle. So there was a thread running along. It was here. We don't care how it got here, but we basically started observing it when it was here. It did some memory changes. Like here, it was doing some memory changes, and then it did a release. That published all of these changes, made them visible. How do we make? But only it made them visible if you opt in into this protocol. How do you opt in? Here comes our other thread. It does the acquire barrier, and it sees this write. This write was the release. Whatever was written, this second thread reads it and says, okay, I see this. I know that I am basically at the same point or actually anytime after, because like this, this was written, I see this value, so I am at the same time or after when this was written, and I have the guarantee that whatever was written by the first thread, if I start reading it, I will see these. I may also see something else, but I have the guarantees that this will be visible. Now, if you put them both together, this is exactly what the locks do. So anything that is in the critical section will be. So the critical section is between the lock acquisition of the lock, which has acquire barrier, and the release of the lock, which has the release barrier. So putting the two of them together gives you this guarantee that any memory modifications you did while you were under lock or while you were between the acquire and the release barrier will be visible to someone else if they wait until you release the lock, acquire it with an acquire barrier. They'll have the guarantee that whatever you published inside your critical section, they can read inside theirs. If you keep modifying this stuff outside of the critical section, they may or may not see that too. So obviously, don't modify shared objects outside of the critical sections. Okay, is that clear? Anybody has any questions on that? Yeah.
So for read, modify, write, you do acquire, read, modify, modify, and then the release is the write that makes it available to everybody else.
Well, okay, so operation itself, again within C++ memory machine, not on any particular hardware, can have no barriers at all, in which case the only guarantee you have is read, modify, write will be done atomically. If two threads do the same read, modify, write, they will not capture the same starting value. See, atomicity works without any barrier. So if you do plus plus, starting from 0, atomically, you will always get 2 on that. That doesn't require any memory barriers. Now, memory barriers come in when you have multiple variables. So for example, so now I have x starting from 0, and I'm doing plus plus x on 2 threads. I will get 2 at the end, in one order or the other. But now I'm using that x as an index into the array. And before I plus plus x, I'm constructing the elements in the array. Will I see that constructor's rights committed to memory or not? Now for that, you need the barrier. And yes, the release part tells you that the one I constructed will now be visible to everybody. The acquire says the ones that were constructed by others, because you read with acquire, so you know where they stopped, incrementing their index. The ones that were constructed by others will be visible to me. Altogether, it basically says I can publish mine and I can see what everybody else has published. Technically, increment can have just acquire, just release, and acquire release in C++ memory model. Whether the hardware supports it is a different story, but in C++ virtual machine, you can do atomic increment with no barrier at all, with either side or with acquire release. Okay. Now, why does it basically why does it happen to me? Okay, here's why it happens to you. Happens to you, well, okay, compilers can reorder the code, but that's a language thing. We could provide language facilities to stop them from doing that. The real problem is hardware reorders the code, and visibility across cores is limited. Why does hardware reorder the code? Hardware reorders the code for a very simple reason. It has to give you good performance. Modern CPUs are massive math engines starved of data. That's just how hardware is built. It has a lot more compute capacity than you could ever feed the data into it in practice. There is one of the solutions CPU designers come up with to reduce this data crunch problem is out-of-order execution. Out-of-order execution is basically a way for the CPUs to find work while it's waiting for data. So here is your program order. You load something, and you'll have to wait for it to make its way from the memory. And then you have some stuff going on here. So you do want to increment this thing that you loaded, but you also have some operations on registers that are later in program order. Out-of-order execution, CPU peeks into incoming instruction stream and says, okay, I have to wait for the load to complete, for my data to arrive. But there is this multiply that applies to 2 things I already have in the registers. The registers are different from the ones I'm loading. Nothing stops me from doing it. There would be no observable difference. The results are the same. Let me pull that in over here. From here, let me pull that in and do it now. That's the out-of-order execution. Okay, the big part of that component, of that out-of-order execution, is this thing called reorder buffer. The reorder buffer, it basically facilitates that out-of-order execution. Okay, there are 3 stages to it. There is issue, instructions enter the buffer. It's a circular queue. Instructions enter the buffer in strict program order. As they're being read from memory, they enter the buffer. There is execution. CPUs peek at the reorder buffer, yank out things they can execute, and do that. And they can execute anything that has all of its dependencies met, in any order they want. And then there is retirement. That's when instructions exit the reorder buffer. Now, that again is done in program order. Okay, here is the order buffer for, for our instruction stream. So this is the issue. You stick in the instructions here. They sit in this program queue in order, and all of our cores. So all of this is for each core. So on this core, there are multiple compute units. There are memory writes. Basically, there are all of this math and memory access circuits on the CPU. They reach into it. They grab whatever they can execute and they do it. When it makes its way around the queue, it has to retire. So it cannot retire before it's executed. So if you reach to the end of the queue and you haven't executed this instruction, the whole thing stalls and waits for that instruction to execute. But if that instruction was already executed, when it reaches the head of the queue, it retires. It's done. At this point, it's done. All of its results are fully committed to memory if there was a memory change. But the out of order part happens because execution units, the entering is done in program order, retiring is done in program order, execution is done in whatever order they want. Anything that that is satisfied by where data dependencies are satisfied is fair game. Okay, if you can execute out of order, what do you do with memory writes? Well, that's where the second piece of the hardware comes in. There is the store buffer. And the store buffer, so memory, we think, the classical picture and what I've shown you before, memory writes go into L1 cache. No, they don't. Because once you modify something in cache, you can't take it back. So there is a store buffer. All the writes actually go into the store buffer, and then from there they eventually trickle their way into the cache. There are a lot of optimizations that happen here, mostly for performance. So, for example, there is the coalescing of writes. 2 writes to the same address, the second one overrides the first one. This one will never make it to cache. The write buffer itself coalesces these. There is this interesting optimization called store to load forwarding. If you need this value again and it hadn't made its way into cache, there is a way to pull it out of the store buffer directly back into the register. And that's much faster than going through cache. Yeah?
Just to show up some understanding for me, isn't that one of the reasons why the store buffer was made? So that
it is one of the reasons why store buffer is made, yes.
Just because when you write stuff to the cache, obviously the cache coherency protocols take effect, and then that causes additional overhead, right?
Yes, exactly.
While the store buffer is there, if you need to use the data again,
yes. Yeah. This is basically done for the whole store buffer is basically for performance reasons. Now, when do the writes actually get committed to cache? Well, that actually varies on different platforms. On x86, it's strictly in the order of retirement. So only when instruction retires can the store buffer flush whatever that instruction wrote into the cache. On ARM, any order you want. Yeah. Okay, now when does it actually get transferred into cache? Actually, whenever the L1 cache has a spare bandwidth. There is basically no particular rule about it. There's one more thing for the store buffer, which is if you are in speculative context when it comes to branch prediction, you cannot commit to cache yet because there is no undoing right into memory. So if you are on a branch predictor in a speculative context, you cannot yet commit that into the cache. But speculative context is kind of a different thing. Has an interesting interaction with concurrency. I'll talk about it in my afternoon talk. But for the most part, other than being a speculative write, whenever cache has spare bandwidth, you flush into it. That's all fine until you hit it with a memory barrier. Memory barrier actually forces the flush of all of that. And that's how it guarantees the visibility. Because everything store buffer is actually not even the part of your L1 cache. It's part of the CPU core itself. It sits right near the registers. it's not visible to anybody. How you guarantee memory visibility? You have to flush the store buffer. You have to at least flush it into L1 cache, at which point cache coherency protocols take over. We'll see those next. But at least it has to make it into L1 cache, because your store buffer is like inside the CPU core, right next to the registers. Nothing can get to it. Yeah.
Is that the case for all memory barriers, or is it just sequential consistency?
No. This is the case for release.
For release? Okay.
Well, for release, you have to flush memory. Release is the one that guarantees that everything you wrote becomes visible.
Okay.
So any memory barrier that includes release would do this.
Okay.
And in fact, that's the main thing it does. There is also effect on the cache coherency protocol, but that's like the primary thing, because these pending writes here, there is absolutely no way to get to them from any other core.
Okay.
All right, now let's talk about cache. So you flashed your store buffer, which means your data made it into your L1 cache. Well, unless you are on an SMT system, nobody else can see your L1 cache. On an SMT system, your SMT sibling can see your L1 cache, which isn't a great guarantee either. If my program is correct only if by accident the two threads are landing on the same core. Not a great correctness guarantee. So now we have to have some kind of cache exchange. So basically this is how it works in concurrent system. So you have core 1, let's say it reads the value of A from a cache line, hasn't been read yet. Well, you have what's called cold miss, fetches all the way from main memory. Okay, now it's in that cache line is in L1 cache of core 1. You read the value of B. It's very fast. It's already in your cache line. Now core 2 wants to read A. It's actually over there, which is not shared. So what you do is you have to traffic that cache line through the nearest shared level of cache and make it here. Into this core as L1. You want the second write, it's fast, or read. So, okay, so this is this bouncing of cache lines between. How is it actually done? All right, where are we on time? Okay, we have time. Anybody saw this acronym before? Yeah, okay, half of you did. All right, modern cache coherency, well, semi-modern cache coherency protocol. These are actually stand for the 4 cache states that are in the protocol. Okay, so we are in our initial state. We loaded this cache line into core 1's L1 cache because this was the first time anybody ever read this. It's exclusive to the core 1. Cache line is in the E state. Core 2 now wants to read. How exactly it's organized in hardware varies from platform to platform, and even on the same platform, like your x86 desktop and 256 core large-scale x86 server have different machinery for doing, how part. Because if that server on your desktop, 16-core desktop, it's just straight up fabric from connecting all the caches. You try to do that on 256 cores, it'll melt the CPU. There's just too much power going into that silicon. It's N squared, basically, logic. So they have directories, bus snooping, all sorts of things. But anyway, what happens is there is a communication between these caches, and they all drop their state from exclude. Well, these didn't have the copy. So now the other core acquires the copy of this line, but the one that was exclusive drops into shared, S. Okay, now core 1 wakes up and decides to write into it. At this point, it goes into the modified state because this is different from what it is in the main memory and anywhere else. Core 2's state is no longer shared. It's now invalid because the value it sees is out of date. So again, there is this interaction between caches that is arranged differently on different hardware, but core 1 sends the signal to core 2 to invalidate its cache line. The way it's done is with this called read for ownership. So writes actually include this hidden invisible read. You do an extra read, but it's called read for ownership. You don't just do read. You say I want a read and I want exclusive. It's called read for ownership. That read for ownership is sends a request to all other cores. They flip their cache line to invalid state, and then they acknowledge it. They send a signal back. That's actually a weird part about this whole cache coherency. Writes, your simple, not contended writes. We're not talking about looping on a spin lock until it changes. It's just a plain write. They're slow. And the reason they're slow is actually because of the light speed. CPUs are large enough that it takes time for the signal to travel from one end to the other, and you have to wait for ACK from all other cores before you can actually get exclusive. It kind of becomes, momentarily becomes exclusive and then modify it. But in order to become exclusive, you have to wait for everybody to acknowledge that they invalidated it. Okay, so that's the M. If you read again, what happens is, so this now has the only correct value of this variable lives here. Core 2 wants to read again. It has to get that correct value. Okay, it knows that it's invalid. So what happens now is it forces the write back. So this has to be committed to memory. Core 2 would read it, and again they go all to shared. So that's the cache coherency protocol. Yes,
So,
let's start from here.
so when modifies goes to shared, right? So the cache line is directly handed from core to core, right? Second core.
In this language, no. It's committed to memory through the write back and then handled to core. That's why I said semi-modern cache coherency protocol. So we'll get to the next slide. If you still have the question, then ask me. Okay, yeah.
In step 3, if then there are multiple writes by core 1, is then the second and third read cheap again because it knows I'm in the modified state, I have exclusive ownership?
Yes. Yes.
So it's only if it changes.
The transition from S to M is expensive, or S to E is expensive.
Yeah, but M to M to M to M.
Yeah, that's all found. Yes.
When we talk about contention, is it manifesting at the request for ownership and acknowledge conflict resolution?
It could be it could just manifest itself in this. So there are different forms of contention. Most of the time, people talk about just the cache line bouncing. Basically, that it was modified here. If you want to just read, it will be shared. But if you want to write, it will become modified here, and it will be bouncing. So most of the time, that's what people do. That's what happens when people talk about contention. But yes, there is this hidden contention that almost nobody talks about, which is on the plain writes. There is the wait for RFO.
And a follow-up. I'm assuming there's some kind of conflict resolution algorithm for agreeing on who requests ownership.
Well, only in the sense that, like, if you're doing atomic writes, one of them will win, and they cannot both win, so there will be no byte tearing. But there is no other conflict resolution in the sense if you're both doing atomic writes, one of you will stomp the other one.
Okay, so it's okay.
That arbitration has to be arranged by the program. Don't blindly do atomic writes. Look at what you're stomping. Yeah.
I don't understand why modified is different from exclusive. Like, why can't it?
Exclusive means you have the same value as it is in memory.
Okay, it's same memory. Okay, got
Yes.
it. So it can be different. Modified is
Modified
different.
means you need the write back.
Okay. I got it.
Okay. Back to your question. I said semi-modern protocol. Modern, but not entirely super modern protocol. There is that, I see. The only change is in the last step. When core 2, so we were here, core 1 had it modified. core 2 wants to read. There is this new, before we went into fully shared and we triggered the write back. Moesi adds a new state called owned. We transitioned from modified to owned. Write back is not triggered. What does it mean? Memory is obsolete at this point. Memory is out of date. The only correct copy of the value lives here on the owned core. How does this, but the core 2 transitions into shared and gets a copy of the correct value. How does it do that? There is a cache-to-cache transfer. That's what Moesi adds. That cache-to-cache transfer without the write back. Let's say core 2 wants to write. Still no write back. The owned state jumps from here to here. Never gets written into memory until it has to, basically until there is a cache eviction. When the core that is currently owned has to, no longer has room for it in the cache. At that point, it has to flush it into main memory. That's what Moesi does. Other than significant performance gains because that memory thing is slow, conceptually it doesn't make any difference. Yeah?
Okay, so my question was really different. So I asked, suppose you have two different, one is in aim state. You have two cores. One core has the cache block in aim state. Another core asks for it. So definitely the dirty cache block has to be written back to main memory, right?
In Messi, yes. In Moesi, no.
Yeah, I'm talking about Messi. Yeah.
Okay, in Messi, yes, write back.
It has to be write back.
Yes.
So main memory has the updated value, and then when the other core who asks for the cache block, does it get from the main memory or does it get from the core?
That depends on the. So there is no like basically both are correct. There are essentially there are like three possible ways to do this. You could get it from main memory if the two cores share L3 cache, they're on the same L3 cache domain. Then you wouldn't actually, main memory would be just L3 cache, not main memory. If they don't even share L3 cache, you can get it through main memory, or if your interconnect cache, like L3 to L3 interconnect supports it, you can get it through that. That would also be valid. So it's possible for the write back and cache to cache transfers to happen in parallel and independently. Write back is guaranteed, but not necessarily the mechanism they use to communicate. It could be, but it doesn't have to be.
Yeah.
Modern, but not ultra-modern. That's what I said. This is what the ultra-modern looks like. In addition to what we talked about, there are these things called near-memory atomics. ARM had them for a while in the large system extensions, not on Apple Silicon.
Yeah.
But Grace Hopper has them, Graviton cores, Amazon Graviton cores have them. When you want an increment to be done on this core 2, and you don't own the cache line, instead of fetching the cache line, what you do is you ask that core to do the increment for you. Special packet gets sent through the interconnect. If you wanted the result back, you get your 8 bytes of the full cache line, and you never get exclusive ownership of the cache line. If you didn't want the result back, you get nothing. The increment is done. AMD now in Zen 4 and above added also near memory atomics. They're different. L3 memory controller has a math unit on it. When you want atomic increment to be done, you ask the memory itself, please do that for me. The memory controller instantly invalidates everybody's cache lines, set them to I, invalid, and does the increment. Okay.
So Intel doesn't have that yet.
As far as I know, no. My benchmarks on Granite Rapids confirm that it behaves, and this is the latest chip I tested, Granite Rapids, it behaves as if it doesn't. Now, there may be undocumented things going on that, or like even newer things going on. So the Zen 4 mechanism is probably documented. ARM mechanism is documented. For Intel, I don't know. Everything I did for benchmarking this suggests that either it doesn't or it doesn't do anything different for performance. So that's the best answer I can give you.
And one unrelated comment, when you said between two interconnects communication, then there's another letter F, which is forwarding, and a cache line knows if it's forwarded to another socket, L3.
Well, that's yeah. So like at the NUMA protocol level, there is more stuff. But
It's part of message. It's called massive.
Yeah, that's exactly this is by Intel. So Intel has the MESI protocol modified to work as AMESIF, where M stands for forward. So that's a modified version of MESI.
okay.
I think it's only Intel who has that.
Yeah. Well, I'll need to look up what they made difference. Okay. All right. So let's talk about atomic machinery in C++. So we're on the same page. Okay, anybody here who doesn't know like what the atomic is and how to use it? No? Okay, everybody knows. All right, so, okay, I'll just point out some subtleties then. Doesn't have to be built-in types, supports like reads and writes, has other operations supported depending on the type. They add more, so C++20 has wait and notify. Integers have fetch add, C++26 has fetch min, fetch max. Has all the operators overloaded. That's a pitfall number one. Okay, this wouldn't compile because there isn't atomic multiply. This compiles just fine, and we're basically conditioned by years of experience to see this and think that. And it doesn't work that way on atomics. Atomic bool, well, for a change, they didn't do anything extra with bool. It works like anything else. Atomic double is valid, and in C++20 you can increment them atomically. Operators, well, easy to use correctly. If you try to do something that isn't supported, it won't compile. Easy to use incorrectly. Expressions are still work. They compile, but they're not atomic. X equal x plus 1. Easy to use inefficiently. I'll show you in a moment. Okay, very few operations actually have direct hardware support like fetch add. There's no fetch multiply in hardware. You could write one yourself. Like they did fetch max. There is no max instruction in hardware either. Okay, everything that isn't done in hardware is built on top of this one instruction called compare and swap, which in C++ is exposed as compare exchange, and I'll say strong for now. There's also the weak version. What it does is takes two values, expected and new. If the current value of the atomic equals to the expected, and by equal they mean bitwise equality, they just compare the bits, then atomically the value becomes new, and true is returned. If the current value is not what's expected, it writes through the reference into the first argument what the current value is, and then it doesn't make any changes and returns false. That's all it does. So conceptually, this is what it looks like. We take a lock. So it's a hardware lock. Hardware itself takes a lock on the variable. We read it, we compare it. If it doesn't compare, we write it into the old and return false. If it compared for true, we assign new to the value, return true. That's basically the pseudocode for it. Okay, how does it do for real? Well, C++ has this compare exchange strong. There are two more arguments to it that we'll cover in a moment. It has to have a hardware support. x86 in general has the instructions that are easy to pronounce, so like test, move, neg for negate, they follow the common words, so it continues this tradition. This is a common Klingon word pronounced kamja. It means probably give me all your data or die. On ARM, up to version 8.0, you had to do it. Actually, compiler emitted a loop, load, link, store conditional, 32-bit ARM or 64-bit ARM. You get this loop on these special load and store instructions starting from ARM 8.1. They do have a single instruction that, so like REX, that's basically on ARM. They don't have this easily pronounced mnemonic, so I suppose we probably have to say CAS to keep up with the tradition, but that's what they did. There is also compare exchange weak. Okay, we might have to skip that. Only really exists on ARM, and only if you're using this older model. The CAS instruction on ARM, actually, there's only one. It implements compare exchange strong. So compare exchange weak kind of disappears, creates spectacular bugs if you develop on something on system with LSE and then run your code on system with LSEC. Because what compare exchange weak does is it can what's called spuriously fail. Compare exchange strong tells you if the current value is equal to the expected, it becomes new and true is returned. Compare exchange weak says if the current value is not equal to the expected, it definitely doesn't become new and false is definitely returned. If it's equal to the expected, we could either do what you want, replace it, or pretend that it's not equal and still return false.
Question.
Yeah.
So on Apple has CAS, right?
At least the M series do, yes.
Okay.
They have LSE. Now, whether you get that or not, actually, so there's a little caveat here. So I have never tried Apple Client because my Apple machine runs basically Apple's hypervisor and Linux on top of it. So I only know what the general client does. But general client, it knows how to do LSE. If you ask for architecture Apple M3 or Apple M4, it will do LSE. If you ask for native, it will fall back to LLCC.
Alright, so I tested this out yesterday. So I have client 1500, that version, and for M3 model I have, it is using LSE. I tried to change the flag to use different version to force it to use LSE. And
I tried client 20, so I don't know what 15 does. But on 20, you can force it to use LSE, but native uses LLCC.
That's Linux client, right?
That's a Linux client, yes. I don't know what Apple client does. GCC, if you put it into native, like GCC 15 in native, will use LSE. But Apple and Silicon definitely has LSE and works just fine. Okay, why do we want that CAS stuff? Because you can do anything with CAS in a lock-free manner. Here is how to do arbitrary expression atomically lock-free. This is your expression, f of x. You read the value, and then you do a compare exchange. If the value hasn't changed, meaning nobody beat you to this, you replace it with the result of the expression. So you compute the expression privately on your own. If the value has changed, you try again. Log-free, not weight-free, log-free. And you can do any expression here. This is basically how atomic math is done without hardware support. Okay, what about memory order? Well, so I said two other arguments. It actually has two memory orders. One is on success, one is on failure. And you can specify them differently. Okay, what happens if you don't specify any memory order? You get that one, sexCST. sexCST is actually a little stronger than acquire release. What it gives you is it gives you the sequential consistency model. So there is a way to essentially serialize your program. It behaves as if all operations were executed in some particular sequence. In practice, what it boils down to is what's the practical difference between acquire release and sexCST. Acquire release gives you all of these guarantees. What happens before stays before, what happens after stays after, as long as you operate on the same atomic variable. If your different parts of your program use different atomic variables to synchronize each other, sexCST gives you a single consistent order. Just simple acquire release does not. Now, you actually never need sexCST. You can arrange any synchronization protocol you want with just acquire release. You will just have to also created before-after dependency between these different atomic variables. It's okay, if this changed, now I'll read this one. If that also changed, now I know that whatever should happen before happened. Okay. Okay. All right, operators, since they don't have memory order arguments, they use sexCST. That's kind of unfortunate thing about the operators. Why? Well, okay, so here is atomic increment with acquire release versus sexCST. It's different. Yeah.
Just, this might be out of scope, but just going back to like the previous discussion when we were talking about the store buffer, what is the type of overhead that applies with sequential consistency when it comes to that? Is it the same? Is there something extra? How does it enforce?
Okay, sexCST emits these very powerful additional barrier instructions that force global flushes. So it's the extra flush of pipelines that.
Oh, so does it flush all store buffers?
Yeah.
Oh.
Well, on the core that executes the barrier.
Oh,
So the whole thing is still opt-in.
yeah.
All the threads have to opt into the barrier. If one thread has the barrier and the other thread just reads with no barrier at all, you get no guarantee. So none of this stuff is a push protocol. You have to opt in from both sides.
Yeah.
Okay, so there are some differences varies on different platforms. So x86. Now we could talk about x86. Every write has implicit release barrier. Every read has implicit acquire barrier. On ARM, they don't, and actually they're forcing these barriers makes it more expensive, about 2x on the M3 machine that I tested. There is a more important reason to use the barriers you want, and that is the readability. Very important. You clearly state your intentions. If you open the lock, if your first instruction in a mutex has acquire release on it, everybody will wonder what the hell you're doing, because normally you just need acquire on the entrance of the lock. There may be some kind of weird locking protocol that needs acquire release, but you must be doing one of those strange locks that needs acquire release on entry. That's what you're signaling. Oh, then there is that. These compile, a lot of compilers issue warnings, but these compile and they are undefined behavior according to the standard. Wrong direction of the barrier. Why? I have no idea. Okay, let's skip the weak memory order for cast. All right.
So store with an acquire is
UB.
Why is that? Because can't you just have a barrier on its own?
Yes, there is also instruction purely for there is a. So first of all, there is a barrier instruction, and there is a portable way to. There is a thread barrier. There is a portable call to issue it.
Okay.
I don't know why. They were basically mimicking x86 memory model very closely. C++ memory model actually mirrors x86 memory model very closely, but I have no idea why. And there is actually at least one common locking protocol. There's a particular kind of mutex that begins with a write acquire. Okay, let's. Since everybody knows what atomic is, let's skip this. Okay, everybody knows what atomic ref is? Okay, the reason it's actually a very good thing, very useful. Also the reason why we can't have nice things in C++ when it comes to atomics. Okay, so have a 12-byte struct with 4-byte alignment, you put it in atomic. What's the size of it? This is 12 bytes, 4-byte alignment. What's the size of this thing?
16 bytes?
Yes. Anybody else? Anybody wants to say 12?
What architecture? What compiler?
Doesn't. Technically, it doesn't matter. So the answer is actually yes to both. 12 bytes, 4-byte aligned, not lock-free is a valid answer. 16 bytes aligned, lock-free is a valid answer according to the standards. Pretty much all compilers choose option 1. Both are standard compliant. Why most compilers choose option 1? Well, because of atomic ref. Because atomic ref allows you to attach, like it's kind of like attaching a const ref to a non-const object. It allows you to attach atomic reference to a non-atomic object. If you have a non-atomic version of this, an original, this is definitely 12 bytes per byte aligned. If you made them 16 bytes, it's kind of difficult to attach atomic ref to it.
Can you go back? I don't get your argument. Atomic ref was introduced much later, right?
It's C++1, yes.
So why does it affect at all the choice for the implementation of std atomic?
Well, it's one of the. So it would basically be pretty much. It would be harder to do atomic ref. So I mean, you're right that most compilers made that choice before atomic ref was introduced. Both choices are legal. Most compilers did this without padding. This would be legal.
I'm sorry. You need the extra byte alignment for the lock freeness of it?
Yes.
Okay.
So it would be legal to make it lock free.
Okay.
By forcing a lock-free alignment on it.
But then the atomic ref would work.
Atomic ref would be harder to do, and you would be losing 4 bytes on every one of these. Yes.
So how the 4-byte padding is making it lock-free?
Because not the 4-byte padding allows you to make it aligned on its size. So you can't have 12-byte alignment.
Certain instructions are only work with the alignment. Right?
Atomics require full alignment on their full size. So this compiles, and it is atomic. It's just not lock-free. The compiler has to do some trickery behind, hidden tricks. It typically emits a little spin lock inside, but it's not going to be lock-free because CAS doesn't work on this. CAS either takes 8 bytes, 8-byte aligned, or 16 bytes, 16-byte aligned.
Why?
That's basically how all hardware atomicity works. And fundamentally, the problem is if you land between 2 cache lines with one of these, which you can, it's a 4-byte aligned. There is no way to do atomic operations that spans the cache lines.
Even if you have 16 bytes, you still can.
It will be 16-byte aligned. It will be 16 bytes and 16-byte aligned, not 8. So it can't straddle the cache line. Yes.
Yeah, so it would be basically beneficial if I'm on a machine that can do this double word atomic operations, and I care about them for the struct to put another 4 bytes there or force the alignment.
That may or may not force the alignment, and actually also depends on your compiler. So Clang will do it, GCC will not. Very subtle reason for why GCC doesn't do it. The only portable way is to actually use like on Intel it would be the under int 128. The MMX types,
and then manually extract
and then do the bit
when
cast.
I care.
Do the bit cast. That's the only portable way. Although Clang will do what you just said, GCC won't. All right. In the remaining few minutes, let's put it all together to implement a partially thread-safe container. Actually, a useful thing. So we have a container. Let's assume that memory is not reallocated. We reserved a lot of space in advance, or it's a deck type container that doesn't need to reallocate. So memory reallocation is not an issue. Any thread can say that I want size to be n. If necessary, it will grow. If it grows, it's log. It takes a log. So grows is log base. If it doesn't have to grow, then it doesn't grow, but after you made that call to set size, you know that the size is at least n. You want to have the index operator that would index into this range from 0 to n, but your index operator, you want to have no locks at all. So the operator square brackets is unlocked. the grows is locked, but only if it grows. So that's reasonable if you don't grow very often and indexes often. So how do you do that? Okay, so this is basically what we want. We have this array. We have an atomic in it for size. If you call set size, let's say this time it didn't have to grow, but it returned 4 to you. You asked for 4, it said, okay, fine, 4. You got 4. These are safe to access. Now, if multiple threads access the same element without locking, that's UB, but that's kind of client's problem. Let's assume that somehow clients can negotiate this. Maybe each thread has their own range in the table, which is the most common scenario, where basically they all grow this table, but they each grab their own piece of it and never interact with each other. So we're not worried about multiple threads hitting the same element. We're worried about multiple threads corrupting the whole container. Now thread B calls set size, it wants 7, this time it has to grow. These are constructed, default constructed. You get back 7, and you can read safely 0 to 7. This thread doesn't know anything about these. It only knows that it can read safely 0 to 4, but it can read safely 0 to 4. And the key part is the operator square brackets doesn't have a lock. Okay, this is how we basically do it. Okay, so this is think of it as stud vector for now. It's a stud vector that isn't documented in the standard library with respect to its thread guarantees, but it's stud vector for all practical purposes. There is a mutex, and that will be used only to grow it, and there is atomic for size, so we have both mutex and atomic. Okay, the constructor reserves the size in the vector. Let's say it's enough. Yeah.
So if there is no alignment, will it not create false sharing?
Yeah, we're not worried about the performance in that regard yet. Right now we're trying to make it correct. We're trying to make them arrange the memory barriers such that the happens before or happens after, or the visibility guarantees make this thing work correctly. Yeah, and actually what alignment is correct is not a trivial question. Okay, so here is my set size. I'll tell it how much I want. It will return me the value. Whatever it returns, I can safely address. And here is operator square brackets. And so this only locks if it grows. This never locks at all. This is what I want. All right, let's look at set size. I'm going to read the size atomically, and I'm shortening the barriers because they don't fit on the slide. Still memory order acquire. And if it's enough, I'm going to return the current size. I acquired the size, which means I opted in seeing everything that was done by anybody else who did a release of any kind before me. Who did the release? We haven't got to that part yet, but somebody did. Okay, if I failed on the acquire, if I fail on the comparison, I need to grow. For growing, I'm allowed to take the log, so here's my mutex, I'm taking the log. But wait, somebody else might have grown it already between the time I checked and the time I took the log. So now I need to check it again. That's why it's called double check locking. This time I don't care about barriers, I'm inside the log scope, there is an acquire at the beginning, release at the end. I read it again, and if somebody else beat me to growing, I do what I would have done up front if I knew about it. Same thing, I just return the current size. Nobody else beat me to growing. Now I call resize on the vector. It grows, default constructs all the new elements. Doesn't reallocate because we agreed that we reserved enough space. Yeah, how to guarantee it in practice? You don't do it with a vector, you do it with your own memory management. I really didn't want to write student initialized fill and everything that goes into this, so I wanted to steal it all from the vector. Okay, here is the release. The new size is being stored into the atomic with the release barrier after all of these constructors fired. So I'm releasing all the work done by all of these constructors, and anybody who reads my size with acquire, which is actually that, will see, will have visibility into what these constructors did. And everybody reads my size with acquire, because the only way to know how many elements you can address is to call set size, asking for however many you want. It may not grow, but it'll tell you how many you can safely access. And it'll issue the acquire barrier. Yes?
Is that store that you do the release semantics while being inside the lock, is that needed for correctness, or is it only for performance that somebody who grows concurrently with the fewer one that I'm growing does not have to take
Okay, it's needed for correctness, but not for correctness. Well, not for correctness of set size. It's needed for correctness of this guy. No locks here. I'm doing a handoff from inside the locked scope into something that has no locks at all. That handoff is what. So it's this acquire that I'm actually worried about. The release. See, this acquire, if it succeeds, is going to go and read. Is going to go and just index into the data array. I have to have the guarantee that this element of the data array is constructed. The only thing to get, and I don't want to take a mutex, the only way to get that guarantee is to acquire what was released. Yes, Mr.
So you are returning a reference, right? So for this operator, and we guarantee that this operator, so when you return the data, that value, so outside someone can...
Client-side synchronization is client-side problem, yeah. We're assuming that every thread has some way to arrange exclusive access to certain elements. Yeah.
Can I have a question?
Yep.
One slide before that. So when the lockhard goes out of scope and it releases that, can you use the same trick and say you're piggybacking its release semantic and you do the store with relaxed?
No, because very good question. Let me repeat. Could I do the store with the relaxed and use the release barrier of the lockhard? No, and here is why. Remember, I'm allowed to read whatever. See, let's say I did this. Let's say I removed the memory barrier from here. Now everything in here can be reordered, just not past the release barrier. If this size store can be moved all the way up to here, which means some other thread can see that size already changed, but constructors haven't fired yet. What I'm saying is, at the point when you can observe size becoming at S, you have the guarantee that all elements from 0 to S have been fully constructed. Within that locked scope, I need additional ordering guarantees. Yes, a question in the back.
How in the hell do you find a bug when there's a bug?
Okay, we actually use this container extensively in our work. For this, surprisingly simple. Okay, let me see if I have it. Oh, okay, this actually was the last slide. Okay, the last slide actually was this, and the answer is in the afternoon talk. So for this container, the answer is actually surprisingly simple. It's easy enough to reason through it. You basically have to have this discipline that you only access the elements whose existence you know, and there's only one way to know existence of the element. You ask, please make sure that 7 elements exist. And that function guarantees not only that they exist, but that you can safely access them. So basically, essentially reviewing your code for that protocol is enough in this case to guarantee correctness. Now, TSAN would actually, we do the TSAN test. TSAN is fine through this and tells you if you screwed up. The tricky part, and that's where we actually found some bugs over time, is, so I said, that the underlying memory is a vector, just one big contiguous array. Well, that's fine if you don't need to grow it. If you do need to grow it, you can't use the vector. you have to use a deck-like container, which adds blocks of memory without moving existing ones. Because in this schema, you can't move memory because this operator returns you references to existing memory, and you can hang on to them. So you can never move memory. The data structure that keeps track of those blocks is some kind of array of pointers, probably multi-level array of pointers. When you create new blocks, that data structure gets reshuffled internally, making sure that stays in their memory location permanently and doesn't move under any conditions. That's the tricky part, that you can follow the chain of the pointers from the index to the memory block. So that maintaining that data structure, but see, that's encapsulated in that object. So how do you write these things correctly when you have to grow memory? That's the hard part.
Yeah.
How do you use them correctly? Still the same way. There is only one discipline. You prove that you're using data sub I. What's your proof that you have the right to use that I? It's less than the last thing I got from set size. Okay, you're good. That's the
So basically code inspection, but then also TSAN will also catch.
TSAN will check this.
Okay.
TSAN has a bigger struggle with the internals of this in a complex case, but the client side of it is fine. Yes.
Just for short my understanding here, in this design of the table, the locking itself is only for the semantics of resizing, right?
The only part that locks is not just the actual growth. If it has to grow, it locks. If it doesn't, if you ask for 7 and it already is 10, it doesn't even lock.
Okay. Yeah.
Yes.
So the win with this approach here is that in this operator here, we do this load, so that makes that cache line shared, but it doesn't invalidate it.
Well, the win is that you don't. Mutex's locks are expensive. The win is that you can call these without exclusion guarantee. If you put a lock in here, if you just did it to stud vector, you would have to wrap operator square brackets of stud vector in a mutex, which means only one thread can access any element. So this thread accesses only element 0, and that thread accesses only element 5. I have that guarantee at the program level. There is in theory no reason why I can't do that at the same time, but if you did it with stud vector, you would have to put sted mutex on the whole thing, which means only one operator square brackets at a time. That's what I didn't want to do. Okay.
Yeah, so that acquire load there is synchronizing with the release store.
Yes.
Before the mutex lock drops.
Inside the mutex, yes.
Yeah. So is that just that release and acquire obviously they synchronize with, right?
Yes.
If I don't have that release there, I think we already asked this. You drop the lock, that also does a barrier. So is that just the rules are the rules, or is there something that would actually happen?
Oh, if you don't have this release, the hardware will very much reorder this store.
So the incorrectness there is that when I do that load, I will see the sizes change.
The size,
but the objects aren't constructed.
Because remember, from the first picture was the barriers. Now is when our atomic changed. Atomic is this one. So I come in with my operator square brackets and I see, do I already have 7 in the size? Oh yes, I do. I'm going to access element number 6. Element number 6 is still in the process of being written.
Right.
Because without the barrier, hardware can move, and hardware actually will move this because look, this sits in the register, and it started this, it puts the S in the register, it calls this function, all of this constructs stuff, it doesn't actually need the value of S. This can go, there is no data dependency, this can fire on the hardware.
Yeah.
Okay, well, we have to wrap up, but all the other questions offline, but I'll be available to answer them.